Okay, welcome back to what I hope is the last section of 1.3, part 3. In this last section, we'll take a look at some classifications and categories of functions. Specifically, we're going to take a look at the idea of algebraic functions, trigonometric, exponential, and logarithmic, because these are the functions that we use a lot of here in Calc 1. Right? So an algebraic function of x is one that can be expressed as a finite number of that means there's there's a fixed number of them. Sums, difference, multiples, quotients, and or radicals involving x to the end, where n is an integer. Okay. The most common type is your plain old polynomial. So there's your most common type. So basically an algebraic function involves adding, subtracting, multiplying, dividing, and radicals. And if your function contains those, it basically falls in the category of algebraically, or an algebraic function. If we're talking about polynomials, specifically polynomials, look like this. And more specifically, all those n's that you see there in those exponent positions have to be non-negative integers. So a non-negative integer is a 0 or a 1 or a 2 or a 3 and so on. The a's are the coefficients. The first term out here is called the leading term, so then that's the leading coefficient. The last term over here, when written properly, is the constant term because it contains no variable. Okay? And then call the n the degree of the polynomial. Right? The zero polynomial is said not to have a degree, so the lowest degree you could have would be a 1. All right. The leading coefficient test. The leading coefficient test, you might remember this from algebra, was a way that we could look at a polynomial function and determine basically what the graph looks like. And it says that whether the graph of some polynomial, regardless of what all of these terms are, so nobody cares about this one, or all those dots in the middle, or that one, whether it eventually rises or falls can be determined solely based on this one right here. And all we need to know is whether that leading coefficient is positive or negative, and whether the polynomial is an even or an odd. Okay? All of this stuff right in here, all that does is it makes it wiggle in the middle. But this one, the leading term out there, controls the end behavior, which is why that's all we care about. Right? So, this is a end behavior graph of an even polynomial with a positive leading coefficient. And basically what it tells you is on the ends of the graph it's going to go up. Now what it does here in the middle, all that wiggling is all those terms. How many times it wiggles, whether it goes above or below the axis, all of that is controlled by the other terms. But that end behavior is controlled by that first term right there. Okay? Similarly, this is an even polynomial where the leading coefficient is negative. And you'll see that it ends up eventually going down. Right? Remember this from your college algebra? Right? Here I have a leading coefficient positive odd polynomial. Okay? Again, the wiggling here in the middle is controlled by the terms we don't care about. The end behavior is controlled by that leading term. Eventually, as you move to the right, it's going to go up, and eventually, as you move to the left, it's going to go down. Okay? So what's this then? That's just the flip of that guy. That means that that leading term must be negative. Now, the question in your mind is, why do I care? Well, the reason that we care is we tend to use a lot of graphing technology because we're lazy. And that's not a bad thing, but it's a thing. We tend to throw things into our calculator or Desmos quite a bit. How do I know if I am seeing the entire graph? How do I know that if I don't make this window bigger, it's not going to wiggle more out to the right, or it's not going to turn back and go back down somewhere out to the right or somewhere out to the left on my picture? How do I know that I'm seeing the whole thing? And the leading coefficient test here can be used to help us determine that, because we know what it should look like on the ends. And when we see that behavior on the ends, we know that we're seeing enough of the graph. Okay? Okay, rational functions. Well, just as a rational number is a quotient of two integers, a rational function, rational function, is just the quotient of two polynomials. So if a rational number is a ratio or a quotient of two integers, 3 and 4, 3/4, rational number, then a rational function is just when we take a polynomial and divide it by another polynomial. Now, just as in rational numbers, the denominator of that quotient cannot be 0, and in rational functions, the denominator can't be 0. And so we would preclude values from the domain of the function f here that would cause q of x to be equal to 0. Right? All right, I think this is the last thing we have to know. No, we have more after this. All right, so without a calculator, can you make a rough sketch of the graph, including all appropriate information, that is asymptotes, domain, range, all that kind of stuff for a rational function? Now, I know that whether you took pre-calculus or whether you took college algebra, you spent at least an entire chapter doing this. So I'm going to work through this rather quickly. All right, so first off, one on the left, rational function, denominator. I'm worried about the denominator. I need to find out where asymptotes are. Asymptotes occur when the denominator is equal to 0 and the numerator is not 0. So the first thing I'm going to do is I'm going to find out what's going on with that denominator. When is that denominator going to be equal to 0? Does that factor? It looks like it does. I think that's x plus 4 times x minus 2. Let's see, first, outer, inner, last. Yep, gives me my positive 2 at the middle and my negative 8 on the end. And that tells me that I'm going to have issues in my domain at negative 4 and at positive 2. But look at the numerator. Is the numerator the same as that? So what does that mean about positive 2? Because when I plug in negative 4, I'm going to get negative 6 divided by 0. But when I plug in positive 2, I'm going to get something else. Let me write that out so you can see what I'm talking about. If I do f of negative 4, that's going to give me a negative 6 in the numerator and a 0 downstairs. Right? That's no bueno, but that also tells me that I'm going to have a vertical asymptote at negative 4. If I attempt to evaluate at 2, I get a 0 in the numerator and a 0 in the denominator. What does that tell me? Well, that tells me I have a hole in my graph. My graph is going to, and then boop, and then whoop, and that hole right there is going to be at x equals 2. Right. Okay, so asymptotes, domains, ranges. Okay, I've got my domain, so that's good. I know I've got a vertical asymptote at negative 4, so I should be able to kind of start putting this together and make a sketch of this. Let's see. There's a vertical asymptote where? Oh yeah, at negative 4. Let's see. In the original function, the denominator has a higher power than the numerator. That means that I'm going to have a horizontal asymptote at 0. And I have a hole in the graph when x is 2. So there's a horizontal asymptote at 0. There's a vertical asymptote over here at negative 4. There's a hole in the graph when x is 2. But I don't know whether it's like up here and down here, or is it down here and up here, or is it both ups or both downs? So I'm going to need some more information. I'm going to have to get some more information about this graph. Why won't this erase? There we go. Okay. So I need some points. So let's take a point to the right of that vertical asymptote, and because I'm lazy, I'm going to use f of 0. And what is going to be the value of this function when x is 0? Well, the numerator is going to be negative 2. The denominator is going to be negative 8. So that's 1/4. So that's right here. And so if I have a vertical asymptote at negative 4 and a horizontal asymptote at 0, and I'm above the axis there, I know that my graph has to look something like this. Except for right here at 2, there is a hole in the graph. Now I need to figure out what it looks like to the left of that vertical asymptote. So I'm going to do something like maybe say f of -5 and see what the function's value is. Let's see, the numerator, -5 minus 2 would be -7. My denominator, -5 squared is 25. -5 times 2 is -10. -10 and -8 is -18. 25 less 18, what's that, 7? So -1. So it's down here, which means that over there to the left of that vertical asymptote, the graph's going to be down here like this. And so I've analyzed this function. I found its domain. I found vertical asymptotes. I found out where the hole is. I've got a graph of it. The one thing I haven't done yet is, what's the range of this thing? Well, the range of this thing is actually going to be really tricky to find because there is a horizontal asymptote. So I know that y can't be 0. It can be positive numbers up here. It can be negative numbers down here. But there's also going to be a number missing right here at that hole. And what's that y value that it's missing at? And honestly, I don't know yet. There's another number that's missing. And how are we going to figure out that number that's missing? How are we going to figure out what that y value is, what that hole is? And the answer to that is we're going to use calculus. Now, we can't do this problem yet. We don't have enough math knowledge yet. But in the next couple of weeks, we're going to have enough knowledge where we can come back and explore this problem and actually answer that correctly. All right, so I'm going to skip this one, leave it for you to do. If you want to see it, if you need to see it, send me a text, send me an email, and I can write it out for you. But I'm going to leave that one for you to do. I'm going to move on because we're starting to get a little bit behind and we can't afford to. We're already 12 minutes in and we still got a bunch more to do. All right, combining functions. Two functions can be combined in various ways to create new functions. We can find the sum of two functions. We can find the difference of two functions, sum and difference, simply just adding and subtracting two functions. We can find the product of two functions by taking two functions and multiplying them together, and we can create a quotient of two functions by just dividing one function by the other function. And these are all great. These are sometimes referred to as the basic ways of combining functions together, or the arithmetic ways of combining two functions, because it's just basic arithmetic operations: a sum or a difference, a product or a quotient, adding, subtracting, multiplying, dividing. Okay. The interesting way to combine two functions is to use composition. Do you remember composition from your algebra class? When you do composition, the result is called a composite function. Now, towards the end of the semester, about halfway through, maybe a third of the way through, the idea of composite functions is going to come back and bite us. So we really need to be able to identify when a function is a composite function. Okay? Now, this is the definition. I'm going to come back to the definition. I'm going to look at this drawing first, because I think this gives you a better visual. The idea behind a composite function is to take two steps and turn it into one step, essentially. Originally, if I wanted to perform both of these, I would have to start with an x, plug it into g, get an answer, and then take that answer and plug it into f to get a final answer. So I'm just going to make up some numbers here. I would have to start with 2, plug it into g, and find out that g of 2 is 7. And then I'd have to take 7 and plug it into f and find out that f of 7 is now 19. And to get from 2 to 19, it would take me 2 steps, because I'd have to do g and I'd have to do 19. Now, for those of you that missed it, if you're wondering where those numbers came from, I made them up. Okay? Mathematicians are lazy, though. I don't want to have to go from 2 to 7. And then from 7 to 19, I want to go straight from 2 to 19 in one step. Well, the only way to do that is to find a new function, the composite function, that does g and then does f, or the composition f composed with g. Now, this is one of the few places where the origins of algebra still come into play, because the thing on the right is the thing that happens first. Okay. So, what do we do to do composition? We take two functions and turn them into one function. Okay? So let f and g be two functions. The composite function f composed with g, or f of g, is the composite function of f with g. Okay, some language there. The domain of the composition is all the x's in g such that g of x is in the domain of f. Wait, what? Okay, back to the picture. I start here, I go here, and then I go here. But because I have this intermediate step right here where I stop and I move into the function f, whatever number I end up with when I do g has to be a number that works in f. If f doesn't work for negative numbers, then any value over here that would take me to a negative number wouldn't work for the composition. Even though it might work in g and give me an answer, it wouldn't work in the composition because that negative number then wouldn't work in f. So finding domains of composite functions can be tricky. It's not always the easiest thing to do, okay? But it can be done, right? So here's some functions, and we're going to do some compositions. So f of x is defined to be that polynomial there, x squared plus 2x minus 1. G of x is that linear function, 2x minus 3. My job is to find f of g and then define g of f. Okay? F of g says do f first, so f composed with g of x is going to be f of g of x. Now, just like previously, I'm writing down exactly what I'm going to do because I want full credit. I want to make sure that everyone knows that I'm doing what I should be doing. So this is f of 2x minus 3. Okay, now here comes the tricky part. Up to here, most people are fine because all I did was I replaced g of x with 2x minus 3. Now what I need to do is I need to do this. And what does this say to do? Well, this language says that whatever your input is, in this case x, whatever's in the parentheses needs to get squared, multiplied by 2, and have 1 subtracted from it. Whatever's in the parentheses needs to get squared, multiplied by 2, and then have 1 subtracted from it. So what is in the parentheses? Well, 2x minus 3 is in the parentheses. So 2x minus 3 needs to be squared. 2x minus 3 needs to be multiplied by 2 and then have 1 subtracted from it. Okay, so f composed with g of x. So 2x minus 3 squared, that's going to give me 4x squared minus 12x plus 9 plus 4x minus 6, that came from here, minus 1. So if you're wondering where things came from, this is this, this is this, and of course the 1 is just the negative 1 there. Now I need to combine terms that I can combine. So there's my 4x squared. I've got a linear and a linear, so that's going to be a negative 8x. I've got a 9, a negative 6, and a negative 1, so that's a positive 2. Okay. And there's my composite function. F composed with g of x is 4x squared minus 8x plus 2. Now, performing compositions, while challenging, is way easier than undoing it. It would be exceedingly challenging, very difficult, to try to take this and figure out what those guys were. It'd be hard to do. Because it would be hard to see what could have occurred to get you there. Okay. So then what's the difference between f of g and g of f? Well, g composed with f of x is g of f of x. So the notation over here on the left says g happens first. This one says g happens first. This one says f happens first. So that's going to give me g of x squared plus 2x minus 1. Now what does g say to do? Well, the g function says take whatever's in the parentheses, multiply it by 2, and subtract 3. So since this is what's in the parentheses, it needs to get multiplied by 2 and then have 3 subtracted from it. So g of f of x is going to be 2 times x squared plus 2x minus 1, and then minus 3. Distributing 2x squared plus 4x minus 2 minus 3. Gathering like terms. Now you'll notice that I'm scratching out the terms as I'm gathering them up. That's not a mathematical thing, that's a Brian thing. I have missed terms too many times in my career. I like to make sure I got them all, and I found that if I scratch them out, I'm less likely to miss one. Right. Hey, what do you know? We are at the end. We are now done with section 1.3. Remember, this is a review, so if you're thinking, man, he moves fast, I do. And we will move fast in the review. Things will slow down quite a bit when we get to chapter 2. At this point, you should be able to do all of section 1.1, 1.2, and 1.3's homework, at least the first week or so of the course. All right, have a good day.